I'm going to pass it over to Rich Kozia, coordinator of the roofing TRD. Rich?
Thanks, Laurel. This presentation is being sponsored jointly by the Building Science and Roofing and Waterproofing TRG. It's my pleasure to introduce Norbert Krogstad today as today's speaker. Norb is a licensed architect and has been with us since 1983. Norb's expertise is in evaluation and resolution of water filtration, corrosion, cracking, anchorage, and durability problems in building envelope systems. He specializes in the investigation of moisture and condensation problems, and he's the recent recipient of the prestigious ASTM Award of Merit. Norb, over to you.
Thank you, Rich. Today I'm going to talk about cold weather problems in condensation problems in low slope roofs. I'm not going to talk about specific thermal bridges, which obviously occur in many projects. This is more of a global look at two different types of low slope roof problems that we have encountered multiple times, where it would cause condensation that drips into the interior. These are the learning objectives. I'll give you a few minutes to take a look at them. All right, for my presentation, this is a basic outline. I'm going to start out with some real quick, general, basic information regarding condensation problems. And then I'm going to talk about the insulated frame roof systems that we've had problems and mechanically fastened compact roof systems, both of which are low slope, virtually flat, quarter and 12 slope roofs. Condensation basics. Condensation occurs whenever the air adjacent to a surface, the moisture from that air is deposited on the surface. The surface is colder than the dew point temperature of the air. And the dew point temperature is just that. It's the temperature at which the air can hold no more moisture. So whenever the surface is cold, it will cause the temperature of the air to be reduced, and then that water will be deposited on the surface because the air adjacent to it can no longer hold that. The condensation problems will also change when something's changed in the system. Either moisture is added to the air adjacent to the system, or the temperature of the surface is lowered. The moisture storage capacity of the air changes with temperature. So air that's 70 degrees can actually hold 110 at typical atmospheric pressure, 110 grains of water per cubic foot. If that air is reduced down to 50, it only holds 54, or roughly half the amount of water. When it's reduced down to 30, it'll be even less. So if you have air that's adjacent to a surface that is being cooled, you can see if it had basically 54, which is a 50-degree dew point, air, and that's cooled, when it gets to 30, there's more water in the air than it can hold, so that moisture will be deposited on the surface that's below that dew point. So when you're looking at any condensation problem, you pretty much have two questions we're going to ask. Regarding cold surfaces, what's causing the surface to be cold? And regarding moisture flow, how is the moisture reaching the air that's the driving force that's providing the moisture for that condensation problem? So any condensation problem we're looking at, we're going to try to identify those two things. For cold surfaces, it's often related to insulation placement, conduction, thermal bridges, convection, it could be mechanical convection or natural convection, the flow of air across the surface, and radiation, the surfaces that are cooled because energy radiates to outer space. Now, I'll talk a little bit about radiation. It happens primarily on clear nights when the temperature of the surface will be reduced because it's basically radiating to the outer space, which is near absolute zero. So when you see frost on your car on a cold morning, but you didn't think the temperature was going to drop below 32, you may very well be right, because the frost can form on your car even if the air temperature is above 32 because of the radiation in a clear sky. And this has a significant impact on a lot of roof systems. A couple things to keep in mind is that moisture almost always flows from warm areas to cold areas. If you're involved in a condensation problem and you're thinking it's moisture within the walls that are cold that is causing the condensation problem, that's probably not correct, because the moisture has to be deposited on the surface. It has to be, the air adjacent to the surface actually has to have more moisture than the surface that it's deposited on. So it can't go the other way around. So in general, we would look at it in almost every case, moisture is flowing from warm areas to cold areas. The airflow will go from high air pressure to low air pressure. Vapor diffusion will move from air with high moisture content to air with lower moisture content. However, although that's the case, in the years that I've investigated condensation problems, there have been very, very few where vapor diffusion was a significant part of the problem. It's almost always airflow. So I'm going to look at insulated frame roof systems. The typical frame roof system, which is talked about in the code, has rafters, which are sloped members that go from a soffit to a ridge. And there's a certain amount of airflow that's going to occur if you have an open air cavity from the soffit vent to the ridge vent. That air will move through the system, and since, as we talked about, cold air is dry air. And I can't stress that enough, because again, if it's 20 degrees out and it's 100% relative humidity, and you warm that air up to 70 degrees, that's only 15% relative humidity. So there's a lot of, looking at the relative humidity obviously means nothing when you're talking about cold air. Cold air, we talk about cold air being dry, even if it's 100% saturated cold air, because it just can't hold very many grains of moisture. So as that air comes in and moves through the roof system, it'll bring that cold, dry air, it warms up, and if there's a little bit of leakage of air from the interior, it is dissipated by that airflow. This is just this is actually a condensation problem, the wintertime condensation problem we had in a sloped roof, but it was, and I'll explain in a second, but basically we had soffit vents and ridge vents, and they were working well. What actually happened in this case, and we didn't figure it out until a little later, was underneath that deck that you see in the image, there was actually exhaust vents from two very large dryers. They moved cleaned a lot of clothes, and this is a big house, but they, for some reason, had two large dryers. And when they went, they filled that whole area with steam. So in this case, we were actually pulling steam into the roof system. But we didn't realize that until much later, because it was hidden under the deck. There was an air vent on the side, and when you put smoke in there, it worked perfectly. The air drew up and came out the top. And if there was normal outside cold, dry air, again, even if it's 100% saturated, we're still talking about as dry air, that would have dissipated any moisture from the interior, and we wouldn't have had the condensation problem. The problem happens when we go low slope. They don't have that same convection that happens. The case study I'm going to have is a home in Highland Park. This was actually a very beautiful home. It was on the bluffs in Highland Park overlooking Lake Michigan, around a $10 million home, and it had, when you went up to the entrance, it was just, you looked right onto the Lake Michigan from the street. It had views that were just tremendous throughout the house. In this house, there was a swimming pool area. that was about 3,000 square feet. It was an indoor natatorium with a pool bar and other things. What happened was during cold weather, they had water dripping from the ceiling onto the floor, and it was a brown liquid, and it went on their furniture, it went in the pool, and it went all over the floor and throughout the place. They made some openings prior to us getting involved. They made a small opening and discovered that there was condensation throughout the attic space. In this case, it's a nearly flat roof. What it was by attic space, I'm talking about the area where within the roof truss members. There was significant black growth, apparent mold growth on the underside, which was later confirmed to in fact be mold. And the water was collecting on the surface of the polyethylene vapor retarder, which they had on the underside of the insulation. This is actually a view. The black that we see above was just full of mold, and I'll show you in some of the other pictures. It was a solid layer of mold. We had the polyethylene, and we had the craft paper on there. You can see by the stain of the craft paper that there was a lot of water that was accumulated on the polyethylene, and then it flowed through the joints in the polyethylene and into the interior. The basic design of this system was a low-slope roof system, 1/4 inch and 12. It had craft paper facing above the insulation, but it had a redundant second vapor barrier in the form of polyethylene sheeting. The double vapor barriers, and they're that close together, really don't pose a problem unless there's airflow between them, and it really wasn't the cause of the problem in this case. There's also they also had put large roof vents on the roof. It seems that the architect in this case felt that he needed to ventilate the space above the roof. And in the case of a slope roof, like we talked about, this is exactly what you want. In the case of a flat roof, it's not what you want, and we'll talk about that in a second. The HVAC system and return air ductwork was also all placed in the attic. There was incandescent can fixtures in the ceiling, which I'll refer to in a few minutes, were not insulated rated. And there was a high relative humidity because it was a natatorium. This is again the basic roof system. It was plywood deck, roof system with a granular surface, with actually embedded gravel into a flood coat. Bad insulation, the vapor retarder directly above the wood ceiling. When you opened it up, there was moisture that was dripping through. This wasn't even on a real cold day that we could see. You can see there was a lot more staining than that, but it was enough to show the problems that are occurring. There's drops of water all over the underside of that plywood. It was saturated at the time we took this picture. We later went through the rest of the house. Actually, what happened was their hygienist involved decided to take some readings on some of the incandescent cans across the rest of the house. When he did that, he found very high mold spore counts throughout the attics of the whole house. Although it wasn't as bad and dripping in the inside as it was in the natatorium, the problem still exists. In fact, we've been on many problems where this exists that were far less humid than you would have in a natatorium and have the same problem occurring. What happens is, you can see this is the roof system with sort of a graphical representation of the roof system with the large roof vents they had. When the sun comes down, it basically heats the roof, and the air will then come out of these vents. So that air coming out of the vents is replaced by interior air that flows through any gaps that happen to be in the polyethylene and for a variety of different features, including lights and other things. When that air comes in, it's moist air. It's interior air, the outside is cold, so that condenses on the cold surface, which is the underside of the plywood sheathing and within the vent. Wind blowing across the roof does a similar thing. When the wind blows across a flat roof, it creates a negative airspace. That draws the air out of the vents, which again is replaced with air that is pulled through gaps in the ceiling and through the polyethylene and into the roof system where it condenses. This is another picture of the underside of that roof deck. You can see the amount of mold. It was throughout the space. There was mold on the joist, virtually on every piece of wood. The insulation is removed in this picture. The insulation actually had quite a bit of mold growth on it. You also see that there's a duct that's above the ceiling, and that's important because it's another source of moisture. The supply ductwork is pressurized, and there are joints in that supply ductwork. The air comes out of that, and it'll do the same thing. It fuels it feeds moisture into the air above the insulation, and it condenses on the cool surface and drops down. This is just a view of the ductwork. It's a fairly typical joint that's not intended to be a real airtight joint, but even when we've done better levels of joining, there's still a problem when you put pressurized ductwork above the ceiling. So the air comes out of those and it puts moisture into the ceiling. There's also, as I mentioned earlier, incandescent lighting fixtures that were not insulated rated. And when you look at it, in this picture, the insulation is removed, but you can see the vents on the side of the light fixtures. So in effect, what it does, the air is heated by the light. It rises up to the top, it goes out those vents, and it basically creates a chimney that brings the moisture into the attic. So to prevent these problems, the best way to do it is to use a compact roof. Put the insulation above the sheathing. Don't put insulation on a flat or low slope roof below the ceiling space. It's just very difficult to accomplish. If you can't do a compact roof because of space requirements, then the next best choice is to put in spray foam insulation. We have talked about actually trying to pressurize it by having fans that blow cool outside air into the ceiling space above the insulation so that it actually redirects the airflow so that it's not coming from the interior. Problem with that is that you're going to have cold drafts and you're going to have condensation as the air leaks through those drafts. So this is the compact roof. We actually used a 2-ply asphalt built-up roof as a temporary roof and then put the insulation bonded to that, and then we have the roof membrane bonded to the protection board. In this case, I believe we used Densdeck. Okay, so that's a little bit about the flat frame roofs, and again, we've seen this pop up on multiple occasions. One thing, before I go on to the next one, I did do some searching because several of these were lawsuits, and did not find any references that actually promote the use of the insulation below the roof system in flat or low slope roofs. If you look at the code, it speaks in terms of rafters, and it talks about air vents on the low side and the high side. I did find an article by a gentleman named Wayne Tobiason. It came in the Construction Specifier magazine in November of '87 that basically warned against using these systems. But I found nothing that actually supported them. So just sort of a background. It's something that's been used by a lot of architects, but it's really not something that's supported in the code or any reference standards, at least that I could find. Okay, the next one we're going to look at is mechanically fastened compact roofs. The case study is a warehouse in Ottawa. And in warehouses in general, we actually look at a lot of warehouses, and we've seen this problem in several warehouses. Warehouses in northern climates are typically heated in the winter and not air conditioned during the summer. They usually rely on exhaust fans to bring air and move it through the system. This is a view of the roof. It's 1.2 million square feet. It's a very large roof. As you walk on the roof, you pretty much see the horizon, as you see in this picture. As you can imagine, there's a lot of money invested in the roof in this system. What was happening in cold weather again was that water was dripping into the interior. It was dripping through splices in the steel deck, through burn holes in the deck at various areas, and the water could drip down and damage merchandise. This is just some views of the water that was dripping onto the floor, typically in warming periods following cold weather. So long extended periods of cold weather and warming periods. That was the worst, but it happened a variety of other times during cold weather as well. The design, again, a low slope roof, roughly quarter inch and 12. There was a steel deck that was supported by steel joists. There was 3 inches of mechanically fastened polyisocyanurate, only 1 layer. We normally would recommend 2 layers and staggered, but it was only 1 layer. There was a mechanically fastened TPO membrane with 12-foot wide sheets. The 12-foot wide sheets were obviously an economy when you have a roof of this size, and they were only connected at the seams. So they're connected 12 feet on center with a row of anchors. The interior relative humidity was fairly high, and it was under positive pressure. So this is the roof system: steel deck, rigid insulation, mechanically fastened. Again, I'm not talking about thermal shorts in general, but we did have a little bit of condensation on the end of the screws, but that typically did not occur. 90% of the time we had dripping. It was not related to anything from the thermal bridge created by the anchors, although that is not a good practice as well. Then there was the membrane anchors, which, again, because the membrane sheets were 12 feet wide, these were at 12 feet on center. So the source of the leak. What was happening is frost was forming on the underside of the membrane. The frost would thicken during periods of sustained cold temperatures, which made the problem that much worse when the weather got warm and that frost melted. The water flowed onto the steel deck, and it found its way to the low spots and flowed through seams and any holes that were in that deck. The moisture sources, the interior of the space used direct fire mechanical heaters. Now those actually have flames that are visible in the interior. What they do is they draw a very simple, very inexpensive heater, very efficient for heating a space. Air is drawn from the outside and it blows across several flames where the natural gas is burning. That heat is brought directly into the interior. The problem is, not only does it bring the heat into the interior, but the flames, when you burn natural gas, you release moisture, about 2.25 to 2.5 times the amount of 1 pound of gas will release 2.5 pounds of water, 2.25 pounds of water. So there's a lot of moisture that goes. It also releases carbon dioxide. But in these large warehouse spaces, they have carbon dioxide monitors, and if they get too high, they have exhaust fans that kick on, and that helps reduce it. But most of the time, those exhaust fans never kick on. The carbon dioxide does not build up to dangerous levels. The product stored in this warehouse also release some moisture. There's also a lot of forklifts. You can imagine, basically, and carts. A lot of it was all run on propane. It's 1.2 million square feet. The perimeter was 2/3 of a mile, and to get around, people either had bicycles or carts. Very few people walked. It just wasn't efficient. You couldn't get anything done. It's too big of a place. The moisture was also some speculation of moisture from the slab. We did not find a lot of moisture. We did some tests of that. Did not seem to be a big part of the moisture source, but certainly there's some moisture that comes from that. The air pressure differential, we actually have 2 methods. It was under positive interior pressure because that's the way direct fired units work. They bring air from the outside. There's I believe there were 6 units at the top of this 1.2 million square foot roof, and they were near the center, in a line near the center, evenly spaced. The reason the heat distributes is because it's pressurized. The air is blown into the building and it leaks out the doors around the perimeter. That results, because the air leaking out, it distributes the air through the space. So you have an interior pressurization. But to get, and we'll talk about this in a little bit more in a few seconds, to get actual positive pressure to cause a problem, you need an airflow path. Just because the building's under positive pressure, if the roof inflates and stays inflated, you're not going to have a problem because that whatever moisture is in that air is going to condense out once, and then it's only by vapor diffusion that it's going to gradually get in there, but there's not a lot of airflow. And the steel deck actually does make a pretty darn good vapor retarder, not a good air barrier, but a pretty darn good vapor retarder. So as long as you aren't getting airflow, you're not going to get a lot of problems. But there's another thing that goes on in these big warehouses, and that's called pumping action. And I'll show you a little bit more from that. You can see here the roof is inflated. The previous view I showed, it was flat. This was during a windy day, and it was inflated, and it was fluttering some. So what you have is the wind blowing across. It increases the interior pressure greater than the weight of the membrane. The interior pressure by itself was typically not enough to lift the membrane, but with the wind, it was enough to lift the membrane. So what you basically have is as the wind goes over it, it pulls air in from the inside. Now, if it dies back down, that air gets pushed back out. The problem is if that membrane is cold, that air lost its moisture when it was in the up situation, and when the air was blown out, it fills back up with fresh, moist air, continuously increasing the thickness of that frost layer. And that's what we call pumping action, because you're basically not developing an airflow path. You don't have an airflow path from the interior to the exterior. This is a huge membrane. There isn't a lot of penetrations in it, and there isn't a lot of flow of air. But this is a big part of the area of the roof. You see this inflating during high winds, and it's because of a few things, not least of which is that the membrane is only attached at 12 feet on center. So the airflow from pumping action, it's going to pull through any seams, burn holes, abandoned screws, any gaps in around any penetrations, and the wall to roof at the perimeter. But again, with the size of this roof, you're pretty far away from the perimeter. The interior pressure, as we said, can also cause a problem, but that has to go in and come out somewhere. So you need to have perimeter or other places where the air can go through. It was not the major part of the problem. Based on our study on this, it seemed the pumping action was the biggest part of this problem. So when it goes, the inflates, the air moisture from the air condenses on the underside of the membrane, like we show here. It can pull in around the edge of the joist through the deck. Again, this at the perimeter, there is some air that leaves to the outside. In the field of the wall, all the splices and burn holes, and then it goes to the joint and the insulation. Again, it's only one layer, not two layers of staggered joints. And if we look at those splices, the seams on the other direction of the metal deck, it goes through those as well. When you get to, weren't a lot of roof penetrations, but for some of the exhaust fans and then for the direct fire units and for roof hatches and other things, there were areas where the air could go in at those as well. The sustained cold temperatures occur especially when they use cold membranes in northern climates. I know you'll read a lot of things about that cold membranes are good in all climates, but they're not thinking about warehouses. The problem with the warehouse, as we talked about earlier, it isn't cooled in the summer. They use exhaust fans that make up air around the base that's a little colder because it's in the shade, and that's how they control the climate in the summer. So there is no cooling load in a warehouse. So in a northern climate, if you use the white membrane, all you're doing is losing heat during the winter that otherwise could have been used to heat the interior space. So although white roofs might have advantages in a lot of buildings, they don't really make a lot of sense in warehouses in northern climates. The white TPO has a very high reflectance, so it's going to not heat up during the day, but it also has a pretty high emissivity. So when a white roof is exposed to a clear nighttime sky, it's going to cool down quite a bit. Emissivity is the rate at which the heat from the roof is able to be dissipated to the nighttime clear sky. The melting will occur either due to solar radiation or rising temperatures. This is a diagram from basically Sarnefeld. I also actually had another diagram, another table that I put up from a few other references. You can see in here that the black EPDM has a very low reflectance. It absorbs 94% of the energy, and its emissivity is around 0.9, around 90% of the idealized black body. The smooth built-up roof is very similar, and in this case, a PVC membrane, but virtually the numbers are the same with TPO. It has fairly high reflectance and also pretty high emissivity. So it has both. So it's not going to heat up, and it's going to release a lot of its energy at night. So the solutions that we reviewed were to correct this problem. One, to eliminate the airflow paths. If we could make the steel deck work as an air barrier, we could solve the problem. We can also try to control the air pressure differential. The problem with that is if we're looking at it, the direct fired units really need that positive pressure to work like they're designed to work. So you really just can't get rid of the positive pressure. We could try to avoid sustained cold temperatures, but that would require doing something like changing the entire roof membrane, which is, as we'll talk about, is eventually what was chosen. Or you can do a combination of those. The first attempt for the majority of the building was to eliminate the airflow path, to use the steel deck as an air barrier by trying to seal all the seams and all burn holes and all the other things in the deck. It was later looked at as part of the final solution to try to do an air barrier directly above the roof deck. First, let's talk about the attempt. It did not work, and part of the problem is it's just a huge building. Around the perimeter, they used spray foam. There was later sealant that went over the seams. This was taken a little earlier. So some of the spray foam was done first. Then there was sealant that was placed over all the penetrations and all the seams in 1.2 million square feet of roof system. It's just very difficult to have the level of care that you need to make this a perfectly sealed membrane. And with the forces involved, it has to be nearly perfect. And so you can see some of the sealant in there. So another way to control the air pressure differential, we talked about making the building neutral or positive, which is 0.2, which really isn't practical with direct fired units. With the pumping action, the best way to do it is to stop the membrane from lifting up. We could do that again by negative pressurization, but not practical due to the system. And I keep saying that we did look into changing the system out to indirect fire. The cost of that in just maintenance and just heating alone was huge because direct fired units are roughly twice as efficient as indirect fired units. And so there would have been huge long-term costs associated with that. A balanced membrane was considered, but as a lot of these big boxes, they used their sharpened their pencils, and there's no reserve capacity in these systems. They are engineered down to the last bit of steel that they can reduce. A fully adhered membrane is a very good solution, and it requires taking out the whole membrane. We also looked into going with low reflective membranes. In the end, going with high absorptive membranes, low reflection, that was not chosen. We were actually working for the contractor, so the owner is the one who actually, their consultant actually made the decisions, and we weren't completely on board with all the decisions. Not that there was anything wrong with it, we just thought that we could have actually done it a little cheaper. And when you're talking about this large of a square foot, every 50 cents or 10 cents per square foot adds up quickly. What they ended up doing was to remove the entire roof system, including the insulation. They put dense deck directly over the steel deck and put rubberized asphalt over that. They then put a layer of mechanically fastened polyisocyanurate, which was anchored through the rubberized asphalt membrane, which was intended to be self-healing. And then they put a second layer of polyisocyanurate that was with staggered joints that was adhered with foam adhesive like Instastick. And then the roof was put on top of that. They controlled the air pressure pumped by also fully adhering the roof system. So this is what it looked like originally, and this is what it looked like in the repair. It's a steel deck, the dense deck, primer, the air barrier, the 1.5 inches of insulation, the anchors, the adhesive, another layer of insulation with staggered joints, more than the membrane adhesive in the membrane. Well, we had talked about doing this because they were having to phase in a very small area. One of the reasons for putting dense deck down in a system like this is because of construction traffic. But when you're doing a phased area where there's very few people working on it, we actually looked into and did some study on just doing the membrane directly applied to the flutes. It actually has the advantage of making it much easier to also see when you're putting in the insulation anchors at the edge of the repair area. You can see where the flutes are, and we really want to catch them on the upper part of the anchor if possible to sandwich that membrane and have the self-healing work for us as best as possible. We also wanted them to reuse the 3-inch layer of rigid insulation. They actually discarded it. There was really nothing wrong with it, but they had some concerns that there might be mold spores on it. We never really saw any. And what we had proposed to do is build tents and actually let it dry out. Again, the size of this roof, they could have had enough for the one phase and let the other phase dry out while any moisture that was in there. It typically dried out very quickly once they took the roof membrane off. But in the end, they used 2 brand new layers, had less insulation. They went with the dense deck. So it added, again, probably more than $1, definitely more than $1 a square foot from all that. And when you're talking 1.3 million, 2 million square feet, that's a lot of money. But this is the way it looked like in the end. You can see this is the edge. You see the flutes, the dense deck, and the rubberized asphalt, the anchors, which are lining up with the flutes, and that was it. So in summary, both of these problems are somewhat similar. They're both occurring in cold climates when interior air is permitted to flow above the roof system. In the case of the frame roof, there's an airspace above the insulation, which, again, if you do vent it, you're probably going to make things worse. If you don't vent it, there's still a possibility of air flowing in there because the system is not perfectly airtight, or it's very difficult to make perfectly airtight. In the case of the compact roof that we looked at, the pumping action was one of the bigger causes of the air movement. When it pulls it up, it brings the air above the insulation where it can condense on the inner side of the roof membrane. So theoretically, if you had a perfect air barrier, you'd have no problems. But that's, as we tried to do, even with the method of trying to seal the deck and make it work, it just isn't practical. It's just too difficult to do. It's a lot easier when it's on the top side in initial construction. If you're using the air barrier, there's a lot of talk about calling it a vapor barrier or vapor retarder. I'd like to make sure we correct that terminology, because the steel deck is a very good vapor retarder. It's not a good air barrier. The rubberized asphalt makes it an air barrier. There's a lot of, in the industry, they keep referring to them as vapor retarders, but they're not really functioning that way. It's really, the primary thing is to make it airtight. When it's on the top surface, it's easy to inspect. It's fairly easy to make it virtually airtight. You just got to be very careful with the anchors that go in. So as far as preventing condensation problems in the future, the best is to not place insulation in the framing of the roof unless you have space requirements and you need to go with SPF. The spray polyurethane foam will function reasonably well. We've not seen problems with that. If you're using, on the big warehouse, I would definitely shy away from using mechanically fastened roof membranes, especially with widely spaced anchors, and if possible, avoiding the white membranes altogether if that's allowed by the building code. Again, with warehouses where they're not cooled in the winter, there's really no, in the summer, there's really no advantage of a white roof. And that's all I have.
All right, thanks, Norbert. Now it's the time for questions if you have any. We've already got one here. How much insulation was added to the top side of the roof deck for the Highland Park case study? If insulation is removed from the attic, does the roofing solution meet energy code requirements for insulation?
We actually added 4.5 inches onto the top. We had two layers of 2-inch and a 1/2-inch cover board, and it did meet the energy requirement at the time.
All right. And the next question here says, on the warehouse, did you consider a fluid-applied air barrier directly to the steel deck? If those were not on the market at the time of the project, would you use one today?
It's a good question, but the problem is, first, one thing, we were not, obviously, I think I said, we were not actually in control of the final recommendations on this system. We were looking at a sheet good. I'm a little concerned with fluid applied just because of the size of that roof. I feel it's a little easier in a lot of cases to inspect. I mean, obviously you still have a lot of seams, but to inspect a roof system that is a membrane that is a sheet good, but it's maybe a little bit of a bias. I think you certainly could go with a liquid applied. You just have to make sure you have enough quality assurance to make sure that the voids are eliminated.
All right. I'll give everyone a little more time. Oh, there's another question. It says, in a residential situation, is it acceptable to use a vapor barrier on the inside of the insulation if the rafter joist cavity is fully filled with insulation?
I wouldn't recommend it, partly because you're still going to get air. I assume in that case you're talking about a non-vented. I mean, the problem is, I believe, especially in residential construction, you're going to get airflow through the system. If you don't have a method of soffit and ridge vents to dissipate that moisture, that insulation will allow some airflow through it, but not a lot. I don't think you're going to get enough airflow. That's an opinion. I don't know that I've ever tested it. You might get enough airflow, but I know that the NRCA they actually require an airspace, and I wouldn't certainly not go against it unless there's research to the contrary. I would go, if you're going to go on the underside, I'd either go spray foam. Well, if it's the rafters, you're talking a slope roof, so I have no problem with that, but then you would have to use a baffle of some sort to create an airspace and then have soffit and ridge vents, or soffit and, yeah, probably ridge vent in the case of a cathedral ceiling type situation.
All right. I don't see any more questions.
All right.
Norbert. So was there anything else that you'd like to add before we wrap it up?
I mentioned it a little bit before, but one of the things that I'm hoping that you get out of this is the use of terminology. I run into this so often with we want to really be careful with between air barrier, vapor retarder, or vapor barrier. I typically use vapor retarder. I realize that when it gets small enough to use vapor barrier, we're using those terms of vapor retarder and air barrier correctly. An inset stapled craft paper insulation worked out to be a pretty good vapor retarder. It doesn't work out to be a very good air barrier. I once did like an experiment. I do weird things sometimes in my free time. On my driveway, I had a concrete driveway. I sprayed it with water, and I put a bunch of 2-foot by 2-foot pieces of plastic. It wasn't a windy day, very sunny but not windy day, all over my driveway, and I let the driveway dry. After 15 minutes in the sun, the driveway was perfectly dry except for under every single piece of plastic, there was a nice square that was just about a ½ inch less on all dimensions than a 2-foot by 2-foot area. Most of the moisture did not move. If you have a vapor retarder, it's pretty much by the square footage of area that you end up having the moisture movement, moisture migration. A vapor retarder does not have to be airtight. When we're on our drawings, we really want to make sure that we're using the term air barrier when we're expecting airtight. I think that's part of the problem with a lot of these houses and that use the framed insulation, and even the other thing is trying to just achieve a vapor retarder and air barrier all in one is difficult, and that's why the redundancy of either the venting on the slope roof or the use of spray foam that just doesn't let an airspace be adjacent to materials is usually a good solution.
All right. Well, thanks again, Norbert, for presenting today, and thank you to everyone who participated.